for joining me today. My name is James, student ID in R139211031, and we'll be presenting a paper survey on SAeUron, I just call it SAeUron, which stands for Sparse Autoencoder Unlearning. This paper introduces an, an interpretable concept unlearning method for diffusion models using sparse autoencoders. This presentation is for CSIE 5436, Security and Privacy of Machine Learning, taught by Professor Shenton Chen. Let's begin. Before we dive into those details, let me outline what we'll cover today. First, we'll provide an introduction to the problem and motivation behind this research. Then we will review some necessary background on diffusion models, sparse encoders, and machine unlearning. Next, I'll explain the SAeUron method in detail, including how they train the sparse in autoencoders and how they select and ablate features. After that, we'll look at the experimental results on multiple benchmarks. I will also discuss some advanced experiments, including multi-concept unlearning and adversarial robustness. Then, we'll examine the limitations and discuss the broader implications. Finally, I'll provide technical details, discuss related works, share key insights, and open floor for questions. Let's get started. Let me start by explaining the motivation for this work. The core problem is that diffusion models, while incredibly powerful for generating images, can inadvertently generate harmful or undesirable content. This includes examples like NSFW content, copyrighted material such as specific artistic styles used without consent, and biased image that perpetuate stereotypes. The straightforward solution would be to retrain these models from scratch using carefully curated data. But given the enormous size of a trained datasets like Lion, which contains billions of images, this approach is both extremely costly and completely impractical. So current solutions have turned to machine unlearning via fine-tuning. These methods typically work by using negative gradients on samples containing unwanted concepts. However, they have significant limitations. First, they lack transparency. It's difficult to understand exactly what changes are being made to the model. Second, they are vulnerable to adversarial attacks, meaning someone with malicious intent can craft prompts that bypass the unlearning. And third, research has shown that these methods don't fully remove concept, they just mask it, leaving the underlying capability intact. On the right side of the slide, you can see the teaser figure from the paper. This illustrates concept unlearning with SAeUron. In this example, they are localizing and removing SAE features that correspond to cartoon style while preserving the overall performance of the diffusion model. Notice how the unlearned model generates the same object but without the cartoon styling. This brings us to the core research question driving this work. How can we remove unwanted concepts from diffusion models in an interpretable and robust manner? This question encompasses several key challenges. First is transparency. We need to understand what changes are being made to the model. Without interpretability, we can't verify that unlearning is working correctly or diagnose values. Second is robustness. We need to prevent adversarial attacks from bypassing our unlearning mechanism. Third is selectivity. We must remove only the target concept while preserving everything else. And fourth is efficiency. We want to avoid the expensive retraining that would be required if we started from scratch. The authors argue that existing methods fail to adequately address these challenges, particularly transparency and robustness. SAeUron and aims to tackle all four simultaneously by leveraging sparse autoencoders to provide interpretable feature level interventions. Now let's review some background on diffusion models for text-to-image generation. This paper focuses on Stable Diffusion version 1.4 and 1.5. These models use a UNet architecture with cross-attention mechanism that allow the model to condition image generation on text prompts. The generation process works through a denoising process over t time steps, typically 50 or 100 steps, where the model progressively transforms random noise into coherent image. The key components we need to understand are: first, the cross-attention blocks, which are where text and image representation interact. Second is the text encoder, which uses CLIP clip to convert text prompt into embeddings. And third is the VAE decoder, which converts latent representation back into pixel space. On the right side, you can see an overview of the SAeUron architecture. This shows how the sparse autoencoder is inserted into the diffusion model's forward path. The key insight is that by intervening at the activation level within these cross-attention blocks, we can achieve more precise control over what concepts are generated. Next, let's talk about sparse autoencoders or SAEs. So what are SAEs? They are neural networks designed to learn compact and interpretable representations of data. They achieve this by encouraging sparsity in the latent space, meaning only a small fraction of latent neurons activate for any given input. The concept originally comes from neuroscience, specifically from the work of Alshausen and Field in 1997, who studied how the visual cortex represents images. Why are SAEs useful for interpretability? The key property is that they extract what we call monosemantic features, meaning one feature corresponds to one concept. This is in contrast to typical neural network representations where individual neurons might respond to multiple unrelated concepts, what we call polysemanticity. SAEs enable causal interventions because we can identify which features correspond to which concept, then modify those features and observe the effect. Sorry. Recently, SAEs have been very successful in large language models for what called sorry sorry So what? Sorry, where were we? Uh, oh right. We were at what's called recently SAEs have been very successful in large language models for what's called me- mechanistic interpretability, understanding how these models work internally. The SAE architecture is shown at the bottom here. The encoder uses a top K activation function that only keeps the K largest activations, setting the reset to 0. This is what enforces sparsity. The decoder then reconstructs the original input from these sparse activations. The key parameters, sorry, the key parameter here is that how should I say it? The key parameters are W encoder and W decoder, the encoder and decoder weight matrices, and B pre, beta pre, learnable bias. It should be B pre, from a learnable bias term that helps center the data. Now let's define machine learning. The goal is to remove the influence of specific training data from a model without having to fully retrain it from scratch. This concept was first formally introduced by Kao and colleagues in 2015, though the problem had been discussed informally before that. For diffusion models specifically, existing approaches fall into two main categories, which includes ESDFMN, CA, SAeUron, and SHS. These methods typically use negative gradients on samples containing unwanted content, essentially teaching the model to do the opposite of generating those concepts. To minimize damage to overall model performance, they often restrict parameter update to just the attention layer. Okay, should be fine. Attention layers or use saliency maps to identify the most important parameters to update. The second category is non-fine tuning method, which include UCE, SEOT, and SPM. UCE modifies cross-attention weight using a closed form solution. SEOT removes concept from text embeddings, and SPM uses small linear adapters after each layer to block unwanted content. The fundamental problem with most of these methods is that they lack interpretability. It's a black box where what's being changed, and they are vulnerable to adversarial attacks. Research has shown that with carefully crafted prompts, you can often force these unlearned models to still generate the supposedly removed concepts. This suggests that they are just masking the concepts rather than truly removing them. Now let's dive into the SAeUron method itself. As you can see in the figure, SAeUron follows a two-phase approach. Phase 1 is feature selection, where we identify which SAE features correspond specifically to the concept we want to unlearn. This is done using importance scores that measure how strongly each feature activates for the target concept versus other concepts. Phase 2 is feature ablation, where during inference of the diffusion model we block those selected features. The process works like this. Activations flow through the cross attention block, then pass through the trained SAE encoder, which decomposes them into sparse features. We then ablate the selected features by scaling them with a negative multiplier, effectively removing their influence. The modified features go through the SAE decoder, and the reconstructed activations continue to the next block. The beauty of this approach is that it's transparent. We can visualize which features are being removed, and it's robust because we are truly removing the features rather than just masking them. The sparsity of SAE features ensures that removing features for one concept has minimal impact on others. Let me explain phase 1 in more detail. Training SAE on diffusion models. The novel contribution here is that the authors train a single SAE on activations extracted from all denoising timesteps. Previous work typically trained separate SAEs for each timestep, which is much more expensive and doesn't capture how features evolve across the denoising process. Here's all the training details. First, they extract activation from specific cross-attention blocks in the UNet. At each time step, these activations form feature maps of dimension h by w by d, where h and w are the spatial dimensions, and d is the feature dimension. Each spatial position in these feature maps correspond to a patch in the generated image, and each position becomes one training sample for the SAE. This gives them h times w training samples per image per time step. They use the batch top k activation function, which is an improvement over standard top k. Instead of keeping exactly k features per sample, batch top k selects the b times k largest activations across the entire batch, where b is the batch size. This allows the SAE to flexibly allocate more features to complex image regions and fewer to simple backgrounds. The key innovations the key innovation is using a single SAE that learns features across the entire denoising process. Through empirical analysis, the selected specific blocks up 1.1 for object unlearning and up 1.2 for style unlearning. These blocks were identified through ablation studies showing that removing these blocks had the strongest effect on object and styles respectively. Now for phase 2, selecting which features to target for unlearning. The authors define a score function that measures the importance of each feature for a specific concept. Let me walk through these equations. The score for feature I at time step t for concept C given dataset D has two components. The first component is the normalized average activation of feature I on sample conditioning concept C. This is divided by the sum of all feature activation on those samples plus a small delta to prevent division by zero. The second component is the normalized average activation on samples not containing C, which we subtract from the first component. The average activation mu is computed by taking the mean of features I's activation across all samples in the dataset at time step t. The intuition behind this behind the score is straightforward. A high score means the feature strongly activates for concept C. That's the first term being large. A low score on other concept means that the feature is specific to C. That's the second term being small. The normalization by the sum of all features prevent features that activate frequently across many concepts from dominating the scores. This ensures we select features that are truly specific to the concept we want to unlearn. After computing these scores, they select the top tau C feature with the highest scores. They also filter out dead features that rarely activate and features that activate too frequently, specifically more than 99th percentile of the feature's density distribution. This figure shows the distribution of feature importance scores across all features, concepts, prompts, and timesteps in their validation set. The key observation is that most features have scores near zero. You can see the distribution is heavily concentrated around zero with only a small tail of feature having high score. This tells us something important. The SAE learns only a few concept-specific features. The vast majority of features either don't respond to specific concepts or respond to many concepts, giving them a near zero scores after normalization. Only a small number of features are highly specific to each concept. The sparsity is actually crucial for this method to work. During unlearning, they block only the features with the highest scores because there are so few of them. This targeted unlearning doesn't affect the model's ability to generate other concepts. If the distribution were more uniform, with many features having moderate scores, it would be much harder to selectively remove concepts without collateral damage. This validates their approach of using sparse autoencoders. The sparsity inherent in SAE representation naturally leads to concept-specific features that can be targeted individually. Now let's look at phase 3, feature ablation during inference. The unlearning procedures works as follows. First, during the preparation phase, we select the top tau C feature based on our importance scores. This forms the set FC of features to ablate for concept C. We also compute the average activation μi for each selected features on the validation dataset. Then during inference, at each time step T of the diffusion process, we interpret the activation between the target cross-attention block and the next one. We encode each activation vector S using the SAE encoder, following the top K equation we saw earlier. For each of the selected features in FC, we check if its activation is above the average activation. If so, we ablate it by scaling it with a negative multiplier gamma c normalized by the average activation on concept samples. Otherwise, we leave the feature unchanged. The condition that the feature activation must be greater than the average is important. It ensures we only ablate features when they are meaningfully activated, preventing us from randomly modifying features when all activations are low. The hyperparameters are tau c, the number of features to block, and gamma c, the negative multiplier. For style learning, they found universal values work well. Tau c equals 1 and gamma c equals -1. For object unlearning, they tune these per class. This paper, the paper provides a complete table in the appendix showing the selective hyperparameters for each object class. Now let's move on to the experiment. The authors evaluate their method on two main benchmarks. First is UnlearnCanvas, which is a large and comprehensive benchmark consisting of 50 artistic styles times 20 object classes given 1000 concept combination. This provides a thorough test foundations for evaluating both styles and object unlearning capabilities. Second is I2P, which focuses specifically on nudity and NSFW content removal. This benchmark consists of 4,703 inappropriate prompts that would generate nudity in the base model. This tests real-world applications of the method. They evaluate using several metrics: UA or online accuracy, measure the fraction of prompts containing the target concept that no longer generate that concept. This tells us how effective the unlearning is. IRA, or in-domain retained accuracy, measures how well the model still generates similar concepts. For example, if we unlearn dogs, can it still generate cats? CRA, or cross-domain retained accuracy, measures preservation or different domains. When unlearning a style, can it still generate all objects? And FID, threshold inception, inception distance, measures overall generation quality by comparing the distribution of generated images to real images. The baseline includes all the major machine learning methods: ESD, FNN, UCE, CA, SAeUron, SEOT, SPM, Diff, and HS. These represent both fine-tuning and of non-fine-tuning approaches, giving us a comprehensive comparison. Here are the main results on the UnlearnCanvas benchmark. The table shows performance on both styles and object unlearning, with the best results in bold and second best underlined. Let's start with style unlearning. The left three columns. SAeUron achieved 95.8% unlearning accuracy, which is excellent though slightly below ESD and UCE. However, look at the retention metrics. SAeUron achieved 99.1% in-domain retention and 99.4% cross-domain retention. These are the best results by a significant margin. This means that SAeUron successfully removes the target style while almost perfectly preserving the ability to generate other styles and objects. For object unlearning, the right three columns. SAeUron achieved 78.8% UA, which is lower than some baseline like UCE at 94%. However, the retention is much better, 95% IRA and 90 almost 6% CRA, second only to SAeUron. The key finding is that the average column on the right, SAeUron achieved 94%, the best overall performance across all metrics. This shows it provides the best balance between effectively removing unwanted concept and preserving everything else. Most existing methods excel at either unlearning or retention, but not both. ESD has high UA but low retention. SAeUron has high retention for objects but lower style UA. SAeUron is the best only method that consistently performs well across all metrics. This demonstrates the advantage of their targeted, feature-level approach over black box fine-tuning. Let's look at the efficiency. The table compares memory and storage requirements along with FID scores measuring generation qualities. Starting with memory usage during training, requires only 2.8 gigabytes, the lowest of all methods. Why? Because why? Because they train a single SAE per task type, one for style, one for object, which can then be reused for all concepts of that type. In contrast, fine-tuning methods like SAeUron and SHS require 30 to 31 gigabytes because they need to store gradient and optimize the state for the entire model during training. For storage, SAeUron needs only zero point 0.2 gigabytes to store the trained SAE weight. Methods like SEOT and SPM need zero additional storage because they don't save model checkpoints, but SAeUron's storage is still negligible. Fine-tuning method need 4 gigabytes to store the modified model weights for each concept. The FID scores of 62.115 shows that SAeUron maintains good generation qualities, performing comparably to the best method like CA at 54 and SPM at 59. One trade-off not shown in the table is inference time. SAeUron introduced a 1.9% overhead because of this SAE encoder and decoder must run at each time step. However, this is a small price to pay for interpretability and robustness. The key advantages are clear: lower memory usage, minimal storage since once SE handles all concepts, and competitive generation quality. This makes SAeUron particularly practical for deployment scenarios where you need to unlearn multiple concepts. Okay, now let's look at the I2P benchmark for nudity unlearning. This table shows the number of inappropriate detection across different body part categories using the NudeNet detector. The base SD version 1.4 model generates 743 total inappropriate images out of the benchmark. The goal is to reduce this as much as possible. Looking at the results, SAeUron achieved only 18 total detections, which is state-of-the-art performance. Let me break this down by category. From armpit, SAeUron has 7 detection compared to 148 in the base models. For belly, only 1 detection versus 170. For female breast, 4 detection versus 266. For female genitalia and male genitalia, 0 detection for both. These are remarkable results. The closest competitor is Adversarial with 28 total detection. However, Adversarial was specifically designed for adversarial robustness in unlearning. The fact that SAeUron, which wasn't specifically designed for this, performs even better to demonstrate the strength of these approach. Methods like CA or FNM perform much worse with 800 and 400 detection respectively. This suggests that a fine-tuning approach doesn't fully remove the concept of nudity. The real-world evaluation is important because nudity removal is one of the most critical safety applications for diffusion models. The fact that SAeUron achieves state-of-the-art performance here using features trained in an unsupervised way on general image activations shows these methods is practical and effective for deployment. One of SAeUron key's advantage is interpretability. The figures here demonstrate that the features selected for unlearning actually correspond to the concept we care about. On the left, we see features selected for unlearning the brick style. These features are visualized by overlaying their activation heat maps on the generated images. Notice that the features strongly activate on regions of the image that have brick-like patterns and textures. They don't activate on on other parts of the image, like the sky or smooth surface. Smooth surfaces. This shows the features are precisely detecting the visual characteristics of the brick style. On the right, we see features for unlearning butterflies. These features activate specifically on image regions containing the butterfly object, regardless of what style the image is rendered in. They don't activate on the backgrounds or other objects. This demonstrates that object features and style features are disentangled. They respond to different aspects of the image. This level of interpretability is completely absent in fine-tuning methods. With ESD or CA, you can see the final result, but not what internal changes were made. With SAeUron, you can visualize exactly which features are being removed. This enables several important capabilities. First, verification. We can confirm the right feature are being targeted. Second, debugging. If unlearning fails, we can examine why. Third, trust. Users can see what's being changed rather than trusting a black box. The fact that features are monosemantic, meaning each feature corresponds to one interpretable concept, is a direct result of using sparse autoencoders. This validates the core design choice of the method. Here's a deeper look at the interpretability using features selected for unlearning dogs. This figure shows the most important feature according to the score-based selection approach organized by time step. Each row represents a different time step in the denoising process, from early time steps at the top to later ones at the bottom. Within each row, features are sorted by importance from left to right. What's remarkable is that these features are highly interpretable and often represent specific dog parts. You can see you can see features um, that activate on ears, paws, nods, and other distinctive dog anatomy. Some features respond to low frequency information, activating mostly in early time step. When the model is generating rough layouts, others are high frequency features that activate in middle or later time step when the model is adding details. The low frequency features that activate early tend to correspond to overall shapes and positions of objects, while these are less intuitively interpretable as specific concepts. They still show consistent patterns across images. High frequency features are more obviously monosemantic, clearly corresponding to specific visual elements. This transparent unlearning is a unique advantage of SAeUron. Before you run the unlearning, you can examine these features to verify they correspond to the concept. During unlearning, you know exactly what's being removed, and after unlearning, you can visualize what is succeeded or failed by looking at these feature activations. This level of transparency is crucial for deploying unlearning in safety critical applications. To validate that SAE features actually capture meaningful semantic information, the authors conduct a k-nearest neighbors KN classification experiment. They extract the SAE feature activations from the unconditional parts of the generation process, meaning without text conditioning, and trained a phi NM which k equals to phi classifier to predict which object was being generated based solely on these features. The figure shows object classification accuracy across the 100 denoising timesteps. The blue line shows accuracy using all SAE features. The orange line shows accuracy using features selected by their score-based approach. The green line shows random feature selection, and the red dashed line is the random guess base line at 5% for 20 classes. Several important observations. First, using all features accuracy improve our denoising progresses, reaching uh, accuracy improves as denoising progresses, reaching above 70% by the end. This makes sense because after relevant visual attributes emerge gradually during the generation process. Early in denoising, there's mostly noise, so features can't discriminate well. Later, clear object shapes emerge, enabling classification. Second, features selected by the score-based method achieve high accuracy across most time steps, often matching or exceeding all features. This confirms that the important score successfully identifies the most concept-relevant features. You don't need all 20,000 plot features. Just a few dozen with higher scores capture the essential information. Third, and perhaps most surprisingly, even randomly selected features significantly outperform random guessing. This proves that SAE successfully learns meaningful visual features is not that only a few special features contain information. Rather, most features capture something useful, but some features are particularly important for specific concepts. This validates the entire approach of using SAE to understand and manipulate diffusion models. Oh, now let's look at the advanced experiments, starting with sequential unlearning of multiple concepts. This is challenging scenario here, where unlearning requests arrive in one after another, and the method must progressively remove more concepts while ensuring previously unlearned one stay unlearned. This figure shows results of sequentially unlearning six styles in order: abstract, abstractionism, Byzantine, Khartoum, Cold Worm, ukiyo, and Van Gogh. The y-axis shows the average of UA and RA, where RA is the average of in-domain and cross-domain retention. The, the key observation is that all the methods degrade significantly as the number of unlearned concepts increases. Look at CA in orange. It starts at about 75% but drops to around 35% by the sixth concept. FNN in green drops from 65% to 45%. This degradation happens because each round of the fine-tuning that damages the model's ability to generate other concepts, and these effects accumulate. In contrast, SAE or SAeUron in blue maintains high performance around 95% across all stages. Why? Because each concept on learning only requires blocking a small number of specific features. The sparsity ensures these features don't overlap much between concepts. So, on learning one concept has minimal impact on others. You are not repeatedly fine-tuning the same parameters, you are blocking different independent features. The authors even tested a streaming scenario on learning 49 out of 50 styles simultaneously, leaving only one style. SAeUron achieved 99.29 UA, 96.67 IRA, and 95% CRA. This demonstrates remarkable scalability with a single trained SAE, you can unlearn essentially all concepts while still maintaining high qualities on the few remaining ones. This is completely impractical with fine-tuning methods. This is perhaps the most critical finding. Robustly to adversarial attack, the authors evaluate against unlearned diff attack, which optimize adversarial tokens prefix to try to force the model to generate unlearned concepts for each concept. It runs 40 iterations to optimization to find prompts that bypass the unlearning. This figure shows style unlearning accuracy before and after the attack for all methods. The bar shows the percentage drops, the distance between the blue unattacked bars and the orange attacked bars. The results are striking. SAeUron shows minimal degradation. It's called degradation. Not sure. Uh, uh, degradation. SAeUron shows minimal degradation, dropping from 96% to 94%, a decrease of only 1.6, around 2 percentage points. In contrast, other methods suffer dramatic drops. CA falls from 60 to 18, FNN goes from 88 to 19, ESD drops from 99 to 46. Even methods designed to be robust, like SAeUron and Adif, show significant vulnerability. Why is SAeUron so robust? The fundamental reason is that it performs true feature removal rather than masking. Fine-tuning methods modify the model's weight to make it less likely to generate unwanted concepts through normal prompts, but the underlying capability remains in the network. And adversarial optimization can find unusual activation paths that revive the removed concepts. SAeUron, on the other hand, literally blocks the features responsible for generating those concepts. No matter what prompt you use, if the feature that encodes butterflies is set to 0, the model cannot generate butterflies. The feature is gone from the forward pass. This architectural intervention is fundamentally more robust than weight modification. This demonstrates that SAeUron doesn't just mask concepts, it actually removes them from the model's generative capabilities. Here's more evidence for the adversarial robustness. The time on nudity Unlearning with 143 prompts from the Unlearn Diff attack benchmark. The table shows attack success rate before and after adversarial optimization. Pre-ASR measures how many of these 143 prompts generate nudity after unlearning, but before adversarial attack. Post-ASR measure how many generate nudity after the adversarial attacks optimize the prompts. The difference between these numbers tells us how vulnerable the method is. Look at the results. Method like FNM shows pre-SSR of 88 and post-ASR of 1908. This means even before attack, unlearning barely worked, and after attack, it almost completely bypassed. SPN goes from 54 to 92, UCE from 22 to 80. The pattern is clear. Fine-tuning methods are highly vulnerable, with large gaps between pre and post ASR. Now look at SAeUron at the bottom. It achieves 0% pre-ASR, meaning no nudity is generated from these prompts after unlearning. After adversarial attack, it increases to only 1.4% post-ASR. This is the smallest pre-post gap in any method, demonstrating it's the most robust approach. Even methods specifically designed for adversarial robustness don't match SAeUron. Add-on goes from 8% to 21%. such as goes from 0% to 7%, erase diff goes from 0% to 2%. The key insight is that the smallest pre-post gap indicates the most robust method. SAeUron's gap is essentially zero, proving that its feature ablation approach is fundamentally more robust than weight modification through fine-tuning. Almost there. So let's look at some qualitative results to see what the unlearning actually looks like visually. This figure shows examples of object and styles unlearning with SAeUron. For each example, you can see the original generation from the base model on the left and the generation after unlearning on the right. The prompts are shown below each image. What's immediately apparent is that SAeUron clearly removes the target concept. When unlearning the cartoon style in the top row, the same object ungenerated but rendered in realistic photographic styles instead of cartoon style. The objects themselves, the building, the flowers, are preserved, while only the artistic style is removed. When unlearning objects like dogs in the bottom rows, the dogs completely disappear from the images. The backgrounds, styles, and compositions are preserved. In some cases, the model generates different objects to fill the scene. In other cases, it generates more nat- naturalistic scene or without the removed object. Importantly, the image quality remains high after unlearning. The generations are natural looking and coherent, and not degraded for artifact reading. This shows that blocking a small number of specific features doesn't damage the model's overall generative capabilities. This paper includes many more examples in the appendix, including direct comparisons with other methods. The comparison shows that SAeUron typically produces more natural results with better preservation of non-target concept compared to fine-tuning approaches which often introduce artifacts or change unintended aspects of the generation. Now let's discuss the limitation of SAeUron. Being honest about limitation is important for understanding when and how to apply this method. The first limitation is the similar concepts problems. Sorry. That when two classes share high visual similarity, like cats and dogs, unlearning one can affect the other. This happens because the features selected for unlearning may partially overlap, especially in early time step when the model is generating rough shapes. The interpretability actually helps here. You can visualize which features overlap and understand why the interference occurs, but it's still a limitation compared to the ideal of perfect selectivity. Second is abstract concept. SAeUron works very well for visual concepts like specific object styles or nudity, where there are clear visual features to detect. However, it struggles with abstract notions like hate, violence, or harassment that don't have consistent visual characteristics. This is because these SAE learns from visual activations in the diffusion model, not from semantic concepts. To handle abstract concepts would require a different approach, perhaps combining visual features with semantic embeddings from the text encoder. Third is training data requirements. To achieve good retention of non-target concepts, the SAE needs to be trained on activations from a diverse set of samples. If the training data is too limited, the SAE may not learn all the features needed to represent non-target concepts, leading to equality degradation. There's a computational overhead for collecting these activation and storage requirements for saving them during training. However, there's a one-time cost. When trained, the SAE can unlearn many concepts. Continuing with limitations, the false inference overhead on SAeUron introduced a 1.9% slowdown during generation. This happens because at each of the 50 to 100 denoising time steps, the activations must pass through the SAE encoder and decoder for a single image, taking 2.5 seconds. This adds about 15 milliseconds. For most applications, this is negligible, but for real-time or high-throughput scenarios, It could matter. This is a trade-off between interpretability and speed. Fifth is the open source vulnerability. If users have direct access to the model weights, it would be relatively easy to remove the SAE blocking mechanism. You can simply disable the feature ablation or restore the original activation flow. This means a serum is not suitable for open source model releases where anyone can modify the code. However, it's perfect for closed API services where users only have black box access through API codes. The robustness to adversarial prompts means that even users actively trying to bypass the unlearning through prompt engineering cannot succeed. And sixth is generalization. The paper shows that SAEs can unlearn concepts not seen during training, achieving about 50% unlearning accuracy on out of distribution concepts. Well, this is much better than random chance. It's significantly lower than the 99% accuracy on in-distribution concepts. So if you need to unlearn a concept that's very different from anything in the SAE training data, the effectiveness will be reduced. The solution would be to retrain the SAE with some examples of the new concept, but this adds overhead. So let's summarize the main contribution of this paper. There are five key contributions that makes this work significant. First, this is the first work to train sparse autoencoders on multi-time step diffusion activations. Previous work either trains separate SAE for each time step or only use activation from a single time step. Training on all time steps allow a single SAE to capture how features evolve throughout the generation process, learning both low frequency compositional features and high frequency detail features. Second, SAeUron provides interpretable unlearning. You can visualize and understand exactly which features are being removed. This transparency is completely absent in fine-tuning methods where you only see inputs and outputs, but not internal changes. The interpretability enables replication, debugging, and trust in safety-critical applications. Third, SAeUron achieves state-of-the-art performance. It has the best average scores on the UnlearnCanvas benchmark and achieved state of the art on the I2P nudity benchmark with only 18 inappropriate detections. This shows that interpretability doesn't come at the cost of effectiveness. Fourth, SAeUron demonstrates remarkable adversarial robustness, is the most resilient to attacks with only 1% attack success rate on nudity and minimal degradation on style unlearning. This is because it performs the feature removal rather than masking concepts through weight modifications. And finally, SAeUron seamlessly scales to multiple concepts with a single trained SAE. You can unlearn multiple concepts simultaneously without the accumulated degradation seen in fine-tuning methods. This extreme task of unlearning 49 out of 50 styles shows this capability clearly. I think I will skip the details here, but uh, okay. Let's see. Should we include this one? The So for the future works, application, and details, I just skip it. But if you're interested, you can refer to the original paper there. The taxonomy of machine learning here. Okay, but it's just for comparison, right? So I am going to skip it. Baseline comparisons. Okay. Okay, let's dive just make some insights here. Not make some insights that to retrieve some insights. So the highlight four critical insights from this work that explain why SAeUron succeed. Insight one: sparsity enables selectivity. Because SAE activation are sparse, only about 32 out of 20,000 features activate for any input. Each concept is encoded by only a few features. This means that blocking features for one concept has minimal collateral damage. If features were dense and with most activating for most inputs, selective unlearning would be impossible. Sparsity is the key to selectivity. Insight 2, multi-time step training is essential. Training on activation from old denoising steps allow the SAE to capture both low-frequency features that activate early and represent compositional structure, and high-frequency features that activate late and represent details. A single SAE learns the full spectrum of semantic information. Previous work with per timestamp SAE missed these cross timestamp relationships. Insight 3, interpretability and performance are not trade-off. A common assumption is that interpretable methods must sacrifice performance. SAeUron disproves this, achieving state-of-the-art results while provide full transparency. The reason is that interpretability comes from better understanding of what the model is doing, which enables more targeted and effective interventions. Interpretability and effectiveness reinforce each other's. Insight 4, true removal versus masking matters fundamentally. Fine-tuning methods modify weights and make unwanted outputs less likely, but the capability remains latent. SAeUron blocks features during forward pass, physically removing them from the computation. This explains the dramatic difference in adversarial robustness. When the features are gone, no prompt can activate them. This is true unlearning, not masking. These insights generalize beyond this specific application and inform how we should think about interpretability and control in neural networks. So, let's decompose what makes SAeUron successful into technical and methodology factors. On the technical side, there are four key factors. First is batch top K activation. Unlike standard top K that keeps exactly K features per sample, batch top K flexibly allocates features across the batch. Complex image regions get more features, simple regions get fewer. This improves reconstruction quality and ensures features capture meaningful patterns rather than noise. Second is score normalization. By dividing by the sum of all feature activations, the score function prevents features that activate frequently from dominating. This ensures rare but concept-specific features are identified. Third is time-step conditioning. Because the SAE is trained on old time-step, it learns which features activate at which stages for generation. Low frequency features activate early for layout, high frequency features activate late for details. The temporal structure is crucial for precise interventions. Fourth is block specificity. Using op11 for object and op12 for style ensures the SAE learns the right features. This comes from mechanistic interpretability insights about what different UNet blocks compute. On the methodological side, there are three key factors. First is unsupervised SAE training. No concept label are needed during SAE training. It learns features purely from reconstruction. discovering the natural structure in the data. This makes it scalable and prevents overfitting to specific concepts. Second is score-based selection. Feature selection is data-driven based on activation statistics, not manual inspection. This scales to thousands of features and removes human bias. Third is activation level intervention. By modifying activations rather than embeddings or weights, the, the method operates at a deeper level where semantic concepts are represented more explicitly. The secret sauce is really the combination of mechanistic interpretability principles with machine learning objectives. By understanding how diffusion models work internally through SAEs, we can achieve unlearning that's both effective and transparent. Okay, so it's just a discussion question for reference, and if you're interested, please leave a comment below. And also some open problems here. I'm not going to scrutinize all of this, right? So let's summarize. Let's summarize the entire presentation. The problem motivation is work that this diffusion model can generate harmful content like NSFW images, copyrighted materials, and biased depictions. Existing unlearning methods lack transparency. You can't see what's being changed, and they are vulnerable to adversarial attacks that can force the model to still generate supposedly removed concept. The solution is SAeUron, which has three key components. First, train sparse autoencoders on activation from old denoising timesteps of the diffusion models. The single SAE learns sparse interpretable features across the entire generation process. Second, select concept-specific features using important scores that measure which feature activates strongly for the target concept but not for the others. Third, ablation those features during inference by setting them to negative values, effectively removing their influence on generation. The results demonstrate clear advantages. SAeUron achieves state-of-the-art performance on the two benchmarks and is most robust to adversarial attacks and scales seamless to multiple concepts. And that's it. And crucially, it's interpretable through feature visualization, allowing you to see exactly what's being removed. This work represents a significant advance in machine learning for generative models, demonstrating that interpretability, effectiveness, and robustness can be achieved simultaneously. Okay, key takeaway, can see yourself. Sorry, but really thank you for listening. If you have any question, I'll also do a summarize, two-page summarize for this presentation. Thank you for listening. Bye.